Hi, thanks for joining us today. Today we're going to be talking about slope fields. A slope field is a graphical representation of a set of slopes which we will get from a differential equation. So, if you don't remember, differential equations look like this. Something like this, to keep it interesting. Now, this is a complicated differential equation, and you wouldn't have seen this on your homework from lesson 8-1 or 8-2 because this is not separable. But even though it's not separable, we can find a way to make a representation of the set of slopes. We're basically just going to graph a bunch of little lines. That's why if you look a little bit ahead, you'll see a bunch of, I think someone was calling it connect the dots. So, in case you're having trouble seeing why this is not separable, what's our first step? If you said or thought, multiply both sides by dx, you're right. Bonus points if you remember to keep everything as a group, because we want to be careful about mixing. But you see the only way to get dx with the x squared is to distribute. But as soon as we distribute, we get something like this. And now these two are stuck together forever. If you have an instinct to divide both sides by root y, that's a really bad algebraic instinct. That can't separate the y out. It would just move a y down here, because dividing both sides is dividing everybody on both sides. Right? We'd have to divide this guy by root y, this guy by root y, and now we have the same problem again. So it's impossible to separate this. It's a whole different type of equation. But even though we can't separate it or integrate, we could still use differential equation to plot the slopes. Because that's what a derivative gives us, the slope of a tangent line. The derivative is a slope of a tangent line. So how about you try to find me the slopes given by this differential equation at the following points. Now again, this is a differential equation, so the dy over dx is giving us a slope. So if someone asks you to find the slope here, why don't you try to find me the slope at these 4 points? Maybe even answer this question. Do your best. 3, 2, 1. Here we go. At point A, we have 3, 2. So I'm going to replace the x with 3. So we get negative 3. And replace the y with 2. That's it. That's all there is to it. Easy peasy. Replacing the x with negative 1. Gives us negative, negative 1. Hope you have 2 negatives there. Careful, careful. Which gives us 1/3, positive 1/3, if we simplify. Negative 2 common negative 1, we get negative, negative 2 over negative 1. Negative times a negative, positive 2, divided by negative 1. Negative 2 for part C. And last but not least, if we do part D, we get negative 2 on top, negative 2 on the bottom, which is positive 1. Easy peasy, lemon squeezy. Now, why can't we find slopes when y equals 0? If you haven't yet, please think about this. It's not that hard of a question. What would go wrong if y was equal to 0? We're talking about points like 1, 0, or points like 2, 0. Well, if we had y equals 0, we would have dy dx would be some value of negative x over 0. And we can't divide by 0. That's it. That's all I'm looking for here. You can't divide by 0, so we will not have slopes. Slopes undefined. You wouldn't be able to undefined. You wouldn't be able to actually interpret what that slope would mean. So we're just not going to do it. Which brings us to our fun little drawing activity of today. Find and plot the slopes given by dy dx equals this, our same differential equation, for each remaining marked point. This is just an easy activity. You want to try to graph each slope as you go. So over here, where we have 1, 1, this slope, 1 comma 1, we would have dy dx evaluated at 1 comma 1 would give us -1 over +1, or a slope of -1. So this little line here, we picture as having a slope of -1. Now, if you're having trouble seeing that, if you drew out that line indefinitely, it would have a slope of -1. Can we see the rise? Can we see the run? And that's all that little guy represents. A lot of the ones we just did are on here, but each of these points you should try to graph the slope. I'll do one more with you, but it's really not that hard of an activity. So dy dx at the point 1 comma 0 would be, sorry, not 1 comma 0, I meant 0 comma 1, right here. We would have -0 over 1, which would be a slope of 0. What kind of line has a slope of 0? A flat line, a straight line, a horizontal line. So you graph here, let's make that look nicer, huh? So you'd graph just this nice, straight, horizontal line right there. Go ahead, try to fill in the rest. Do it in pencil, obviously. You might make a mistake. It's not that bad. Do not do anything on the x-axis. You should know why already. Anything on the x-axis has a y-coordinate of 0, so these slopes are all undefined. Spoiler alert. 3, 2, 1. Make sure you finish graphing each slope. I'm going to reveal all of them at once. We're not going to go through the whole thing. I don't want this video to be long for no reason. You should really try. It's not that hard. 3, 2, 1. Okay. So this is my slope field. It should be a little dizzying. Someone I think once called it like the magic eye posters, the 3D posters, where if you look at it cross-eyed, you get all tripped out. So this is a slope field. This is a slope field. This is what it means to be a slope field. Again, I want to emphasize that right here, there's no slopes since y equals 0. That's the line y equals 0, the x-axis. Now, if I want to make solution curves, if I want to sketch solution curves containing 0, 1, actually I want to use this in a different color, and obviously I wasn't circling it right anyway. If I want to have a solution curve containing the point 0, 1, we're going to try to follow the flow of these slope lines starting at 0, 1. So starting here, we're going to try to follow the slopes. Pink was an awful color. I should know that by now. Green. Starting at the point 0, 1, we're going to try to follow the slopes. Now this is a weird technique. This is the most, I don't know what I say about this. It's the most touchy-feely it gets in math, or at least in calc. We're going to try to follow the slopes, staying parallel when I can see a slope, and going through the slope if I have to. We're not trying to connect the dots. We are not playing this game. It is not actually connect the dots. Don't do that. That is not right. That is not a smooth function. And differential equations almost always come from smooth functions. So what do we do instead? We kind of see this as a flow line, like a current. So like we drop a leaf right here, and it tries to follow the current or the flow of this field. So if we drop a leaf right here in this current, in this slope field, where will the leaf go? Well, what this red line means is the leaf will be shoved a little bit this way, and then following what's happening over here, because these should be parallel, we're going to start to bend a bit. We're going to start to bend a bit down. It's easier if you just go fast, to be honest. Now, we don't know what the slope is here, so this becomes a boundary line, just to be clear. This is a boundary. You can't go past it. You can't touch it. When students first get into this, they like to go all the way around. That's not right. We have to stop here. I didn't know the slopes here. And then you can't just go one direction. Make sure you go both directions. Getting something like this. That'd be right. So again, my graph is parallel to other slope lines, and it should be like an average of slopes when it goes between. So we'll do one more together. Our solution curve must be a function. So again, if I did what most students' first instincts is, and I went around, no longer a function because it doesn't pass the vertical line test. I hope you didn't draw that. Whose domain is the largest possible open interval containing the point. That's why I had to go both ways. That's all that means. Make sure you go both to the left and to the right of the point until you can't, until you hit a wall. Sketch a solution passing through -1, 1. That's the next one we'll do together. I guess I want to use a brown. Let's try that. So going through the point -1, -1, 1. Feel free to do this yourself if you feel strong. -1, 1 is right here. You feel like you're getting this. You can't decide if that'll be a bad color. Let's use the tan color. Yeah, that'll show up. All right. Try it if you feel confident. If not, what am I doing? I'm going both ways. So pause the video if you feel confident. I'm going to try to go both ways. So arcing out this way, the leaf gets shoved down, and I'm trying to bend it. It can be a little shaky. The grading can be pretty forgiving. What can't it do? It can't go past that. Do not do that. It would start to become not a function anymore. And then we're going to go this way. It's not going to hit quite at that point. If you made the one going through there, it's bad. We're trying to be really smooth. We're just trying to follow this flow. Picture the leaf on the wind. Watch them fly. It would actually hit this point, but what I'm trying to say is it doesn't really matter. It's forgiven. On the AP test, they give you like a dotted line where your graph would have to flow. Fall in, blah. We did that in tan, not brown. And let's pick a nice blue for this last one. So you really should try this. Don't worry. It can all be erased. Just try it out. Just try to follow the flow line, starting at the point 0, -3. Starting there, go both ways, see what happens. 3, 2, 1. So I get shoved out a little bit this way. That's too high, actually. Shoved out a little bit this way. And then my slopes start to bend me. And I know I'm having a shaky hand right now, but I'm trying to say that's okay. It doesn't have to be perfect. And I notice my slopes are getting steeper, forcing me this way. Open. Going this way. Same kind of thing happening. So maybe something like that. Maybe you were a little smarter. I know a little bit more about this graph. I know that's not really what it looks like. It might have looked more like this if we were being really accurate. Open. If any of these are filled in, that's where you start to lose credit. I don't know. What type of graph does this differential equation seem to be producing? What type are these guys? So if you went all the way around, you might have seen it better, but it's wrong. Each of these graphs should have been semicircles. Now, that's a little harder to see. You're not going to really be asked questions like that. You're not going to be asked to talk about, hey, what does it look like? Does it look like a semicircle? No. But you will be asked to maybe solve the differential equation. Sorry. So, the most common student error in sketching is to extend the sketch too far and create a graph which is not a function. It's important to set appropriate boundaries for your sketch. Why is the x-axis a boundary? One more time. Why is the x-axis a boundary? And it's because there's no slopes there. Slopes are undefined. Since, I don't know, divide by 0. That's why we can't go past there. Do not go past the boundary. You can memorize that this is a boundary. I mean, again, not every example will be like this, but you can memorize how to find boundaries, or you can just memorize not to make something that's not a function. You should know it's a boundary. You should know to make something that's a function. Both of those are non-negotiable, necessary skills. Now you get to solve this. You should already be experts at solving these differential equations. Please pause the video now and try to solve it. Here we go. 3, 2, 1. Did you do it? Did you try it? I can't force you. First step would be to multiply both sides by dx. You could have also just cross multiplied. Hopefully you're starting to see that. Because if it didn't cross multiply, what you would see is like, okay, what's keeping all these x's by being by themselves? We got to move the y. So I multiply both sides by y. And so my first thing I should have really would be y dy equals negative x dx. If I integrate both sides, I'm going to write it out nice, easy. I'm actually showing all my work. Most people would just jump from here to the integral step, which is fine. It is fine to go from this step all the way to the next step I'm about to write in blue. The integral of the antiderivative of y is y squared over 2. The antiderivative of negative x is negative x squared over 2 plus c. We try to keep the c's on this side, the x side, the independent side. Multiply both sides by 2, trying to solve for y. Y squared equals negative x squared plus 2 times a constant is just some other constant. I definitely have mentioned in class to a few different people, if you just change what c is each step, you could. Like, that's an option. That's like a cheating technique. However, you should be able to understand why we want to change the variable. It's because this c cannot be this c. This c1 is 2 times c. Okay? Take the square root of both sides. Y equals plus or minus. I put the plus or minus as soon as I take the square root of both sides. Something like that. Again, I can't emphasize enough, this is not plus or minus x plus c2 or something like that. You can't just take the square root of, because I said this in class and everyone's like, what? Who would do that? But then in real life, what do I see? I see people doing this all the time. That's not right. You can't separate square roots like that. Don't do it. So we either have y equals the positive branch of that square root or the negative branch of this square root. And both of these guys are semicircles. Just so you know. Right? Because our circle starts off like this. So if we solve for y, plus r squared. Right? And this is just some constant. That's just some constant. And when we take the square root of both sides, we end up getting a semicircle. Okay? Because we end up getting a positive version and the negative version, the top half of a semicircle, the bottom half of a semicircle. Okay? Enough said about that. Do the possible solutions verify our results from example 3? You should always run this kind of a check. You should always ask yourself, hey, did what I just get make sense? Does my graph match my derivative? Does my graph match my solution? Does my solution match my graph? If they don't, it's a problem. So let's find the particular solutions for each of these graphs. So if the graph passes through the point 0, 1, we know we want to start off with the positive branch. We want to start off with y equals positive because, and I got a million questions about this, because the y is positive. People were like, I don't know whether to use x or y. We always base it off the y. We want to decide whether the y should be equal to a positive branch or a negative branch. It's about the y. It's based off the y. The x doesn't affect it. So looking at the y value being positive, we'll start off with 1 equals positive 1, positive square root, negative 0 squared plus c1. Solving for c1, we get c1, and c1 equals 1. So we would have square root negative x squared plus 1. You could check, but this is in fact the graph that is a positive semicircle hitting that point 0, 1. Type it in your calculator, you can see. Or you can believe me. Now, between 0, negative 3, again we want negative 3 equals negative square root. Why do we have negative square root? Negative root since y is less than 0. That's the only way to get this right, ladies and gentlemen. The only way to get this right. Negative 3 equals negative square root, negative 0 squared plus c1. 3 equals square root c1. c1 equals 9. So we get negative square root plus 9. Again, the only way to get that negative, the only way to realize that that's the negative you needed is if you check right here using the y coordinate to get that negative. Otherwise, you'd have the positive top half. Otherwise, going back to a graph, just to give you a visual, otherwise you'd have this guy. It's anti-graph. You'd have that one. Some circle, right? I don't know. I can't make it look pretty. I'm not drawing well today. All right. Careful with the signs. End of story. All right. Now, for example 5, we have a differential equation y prime equals 1 over y. Draw the slope field. And again, a possibly good first step is dy over dx, to replace y prime with dy over dx. Try it out. Draw a slope field, 1 for every single dot. Again, there are no dots on the x-axis. Why? Think about it, and I'll talk in 1 second. Think about it. Get me those dots. Get me a slope for each dot. Give me a little tiny line for each dot. Who knows which way it goes? 3, 2, 1. Spoiler alert. Here's what you should have. So we're talking about 0, 1. 0, 1. We would have 1 over 1, or a slope of 1. Positive 1, 1. 1 over 1. You should have noticed as you were graphing that we're getting all of these same slopes if we're at the same y value. Because my slope, my dy over dx, only depends on my y value. X, changing X has no effect on it. So here we go. Graph the particular solutions passing through the points. If you need to readjust your graph, go ahead. If not, here we go. You should try it out. -2, -1. Oops, almost went up. Right here. Again. Oh, I meant to say this on the last slide. Or before you pause it. Slope undefined. Because the y value here is 0. 1 over 0 is slope undefined. So this is a boundary. Boundary. So we're going to go out, hit the boundary, open circle, and we're going to follow these slopes out this way. And it looks like they kind of level off. Something like that. That'd be fine with me. That was -2, -1. You really should try this one out on your own. 2, 2. That's right here. Try it out. See what you get. 3, 2, 1. Here we go. I'm going this way first. I'm going to make sure I touch the boundary. So if you fail to touch the boundary, do you know what happens? If you fail to touch the boundary, it would make it look incomplete. So a lot of people get these nerves up and then they do something like that. They feel like they don't know what's going to happen, so like, let's just stop. I still mark you wrong for that. Anyone should. You have to go all the way, show me the entire graph. That's what they mean by the largest possible interval, and then don't go past it. It's a bit of a spoiler. If you go past it, that's not a function. It doesn't pass the vertical line test. So we're trying to make it look as nice as possible with an open circle that I can see the white inside of. Solve the differential equation. Go ahead, try it out. 3, 2, 1. Cross multiply, again, a really good first step here. Y dy equals dx. The antiderivative of y, dy, you should have gotten y squared over 2. The antiderivative of x is just x plus c. Multiply both sides by 2. Here's what leads to some bad habits. 2 times x is 2x. It's not x1 or something like that. Don't be silly. 2 times c is just a different constant. And we get y equals plus or minus square root 2x plus c1. So which one will we choose for -2, -1? For -2, -1, I will choose my y value. It's based on the y value. I'll choose the negative square root. So for -2, -1, we want y equals negative root. So -1 equals negative root. Plugging in -2 for x gives me -4 plus c1. 1 equals root -4 plus c1. 1 equals -4 plus c1. I squared both sides. And c1 equals 5. So we would have y equals negative square root positive 2x plus 5. That's for this one. And now how about for 2, 2? For 2, 2, we want y equals positive square root. 2 equals square root 4 plus c1. 4 equals square root. Nope, not square root. I squared both sides, and I forgot even what I did. I squared both sides, so the square root disappears. I squared both sides, so the square root disappears. I think I've seen a lot of people on tests just get rid of the square root without squaring the other side. Careful about that. And C1 equals 0, which is very convenient. That means we get y equals positive square root. It's okay to write that plus sign, 2x. Done. You don't want to solve this for x. I've seen that happen sometimes when people get spooked when there's no constant. Solving for x just gives you something that's not a function. Solving for x gives you something that's not a function. Careful. We're going to end with a discussion of multiple choice problems that you could get. Here's one common one. Which of the following differential equations below matches the slope field shown at the right? So this slope field will end up being generated by one of these equations. So what do you want to check for? That becomes a really important question. One thing I want to look at is see how changing just x, or just y affects the graph. By graph, I mean the slope, I guess. So if I keep my y constant, but I move left and right, I'm changing my x only. Think about that until it makes sense. If I look just moving left and right, that's me having a constant y, and I'm changing my x. All of these guys have the same y value. They have different x values. So as I look at this, and I look at each row, we're basically looking at each row of slopes. You notice that each row has the same exact slopes in each of the row, in the whole row. That means for this graph, changing an x has no effect. So that means that I could make x a million bajillion, but as long as I have the y coordinate, it doesn't matter. If the x doesn't matter, the x can't be part of the equation. So that would cross out A, C, and E. And that's how powerful that can be. Checking along just the y would be checking one column. And we can see how each column the slopes are changing. So y does affect the slope. Look how the slope changes as I go down the y. So now we look for other patterns. What do you notice about the slopes here? Something that jumps out to me personally is that my slopes are almost always positive. Now, that might be harder for you to see. You can test points. But sometimes, depending on the point you test, you might get the same answer anyway. But you hopefully look for something that can narrow down to just two choices. If you're narrowing down every question in the AP test to two choices, you are going to pass just fine. As long as you narrowed it down to two right choices. If you can cross out things, if you cross out people, whatever. If you can cross out just a few options, you've increased your odds dramatically as long as you know you're crossing out things that are officially wrong. So we can test points. Let's try 0, 0. We have the origin right there. B, y prime would be 0. D, y prime would be 1 plus 0 or 1. What does that slope look like? Way more like 1 than 0. What would a slope of 0 look like? A horizontal line. These kind of things take a while to get used to. You should try to do as many of them as possible. Here we go with one other style of differential equation. multiple choice. The slope field for a certain differential equation is shown right here. Which of the following is a specific solution to the differential equation? And here my best method for you would be to graph, either mentally or actually on your paper, graph and see how it fits the flow. So you could do this yourself. Check each of these parent graphs and see how they fit the flow. Try to get an answer and then unpause the video. 3, 2, 1. So A, e to the x, starts off here and has real big exponentially growth. That's why it's exponential. Something like that. Does that fit the flow? Absolutely not. Do you see how it goes against the flow? It's really fighting the current in every single spot. So it could not possibly be A. Done. B, e to the negative x. Still has the same first point. It would be a reverse exponential. It would be reflected around the y-axis. That's way too low. I don't know. That looks like a really good choice. In fact, it might be. We're going to hang on to that, though, in our mind. Maybe B. It's okay to put a question mark. No one will notice. Negative e to the x. What kind of transformation does that do to our parent graph? Well, that's a reflection across the x-axis. It doesn't look so bad against many of these slopes over here, kind of over here. It looks really bad against this. So absolutely not C. So Australia's trying to see if something is better than this. Let's jump to E and get that parent graph on there. So E will look like y equals log x, which will have a vertical asymptote right here. That would be the x-intercept, and then it'll level off like that. Now, not really level off, it'll just start growing slowly. Definitely conflicts. And what does negative on the outside do? Again, it flips us across the x-axis. So something like this. Now, the problem is, I didn't graph it right. The problem is these two look really good until you get farther and farther out. So it's kind of hard to tell. It's definitely B. It's definitely B, but it's kind of hard for students to tell when they first get used to this. It's definitely B because as I go this way, I can see my slopes no matter where I started, no matter how high I start. The slopes are always leveling out. They're always starting to level out and get kind of flat. Whereas for this blue one, they never really become flat for 1 over x. Okay? The slopes will always, what did I say? For 1 over x, for natural log x, it always is growing. It's always increasing. But they kind of level off. But they're not as fast as E. Because of the scale, we can see E's leveling off really quickly. Probably by around the time of 2. So as a judgment call, what I want to try to comfort you is if you can narrow it down to 2, you're always okay to guess on the AP test. That should be enough. Try to do your homework. Try some stuff out. It's a really important skill. It's really the last new thing in the whole course. Everything else is just new integration techniques, limit techniques, differentiation techniques. Thanks for joining us today. Have a great night. Have a great day. Bye.